Okay, so welcome back, everybody. So I'd like to finish up my discussion of kind of where geometry headed before getting into uh, people who did work in the underlying foundations of both analysis and calculus, and then even at a lower level than that, at like a more foundational level than that, work on the rigors of set theory, the sets that underlie all of this mathematical language. Um, so I talked about Riemann last time and kind of the direction that geometry went in post Riemann. So as I mentioned, Riemann was unhealthy and he had spent a lot of time in Italy in his later life in an attempt to fix his respiratory problems and his health problems by moving to a slightly nicer climate than that of Germany. So he spent a lot of time in Italy, and in Italy he'd been in correspondence and he'd been in direct contact with students there, showing them everything he knew about this geometry that he'd developed. And on account of that, almost all of the geometry that came out of that time, or almost all of the differential geometry that was developed in that time, is named for Italian mathematicians. So they'd done a ton of work. Basically, Riemann's acolytes in Italy did a ton of work, and if you pour through any of that stuff, you'll find it littered with a ton of Italian names for exactly that reason. So Levi-Civita, Codazzi are just a few, but the Beltrami is another. So Eugenio Beltrami was actually the first to, maybe I'll even write out, was that Beltrami's first name? Now I'm not sure. Let me look that up. I don't know why. I think I may be confusing him. No, that's right. It's Eugenio Beltrami. So he was an Italian mathematician. He lived between 1835 and 1900. And it was Beltrami that came up with a complete and well, what should I say rather than complete? I should say Beltrami came up with a very nice way of fully understanding this hyperbolic geometry. So he was the first to prove the consistency of this. So he was the first to prove the consistency of the non-Euclidean geometry first discovered by Janus Bolyai and Nikolai Lobachevsky. This model that he used is called the Klein-Beltrami model now, is named for him. And it's called Klein-Beltrami for the mathematicians Beltrami and Klein, which we'll talk about here in a little bit. So this is the Klein-Beltrami model of hyperbolic space, of the hyperbolic plane. Okay, which you can have a look at. This was the way he went about showing it. So he was very important in that way. So he did a lot of work with other Italian mathematicians. So just some at the time that I can name drop here. So Codazzi, Ricci, Levi-Civita, and so on are just a few important Italian contributors to geometry. So this was really the foundations of differential geometry. And as I said, this isn't it's not a coincidence, really. It is specifically because of Riemann's interaction with the Italian mathematical community that this came about. Okay. Okay. So one more geometer that I want to mention before moving on is Felix Klein. So Felix Klein was another German mathematician. So he, let me get his birth and death dates. So 1849 to 1925. So Felix Klein is probably most known popularly for the association of his name with Klein bottle. So he constructed the Klein bottle, which was an early example of a non-orientable surface, or a surface that only has one side, or non-orientable surface. So unfortunately, a non-orientable surface like this, this particular non-orientable surface, can't actually be embedded in a nice way in space without self-intersections. So any attempt to come up with a Klein bottle in reality is going to have self-intersections because there's no other way to avoid it. You need at least 4 space dimensions in order to actually properly embed this thing without self-intersections. If you've never seen a Klein bottle, you could Google Klein bottle to see what the shape looks like. But again, those are self-intersection versions. So if you have ever seen one, you'll notice that they look kind of like this. So they have like a neck that kind of looks, maybe I should do something like this. Like there. It's like a neck that passes through itself. Like that. I did a terrible job of drawing this thing. Okay, so there's my version of Klein bottle. You can view nicer versions that have been rendered graphically. Like I said, the Klein bottle looks something like this. Another way to describe it is after a construction named for another German mathematician, which you might be familiar with, called a Möbius strip. So a Möbius strip you can actually construct. If you take a strip of paper, maybe I'll do that on Monday. I actually did it in my Calc 3 class a few days ago. If you take a strip of paper here and hold it at one end, and you orient this thing in such a way that you introduce a half turn and then identify the ends without turning, okay, then what you get is a Möbius strip. A Möbius strip is, again, an example of a one-sided surface. It's another non-orientable surface, but this one has boundary. So it's a non-orientable surface with boundary. Anyway, so Klein did not come up with a Möbius strip. That's named for another mathematician, Möbius. But the Klein bottle can be described as 2 Möbius strips glued together along their boundary circle. Okay, so the Möbius strip has some boundary circle or boundary curve. If you take 2 Möbius strips and glue them together along their boundary curve, you get a Klein bottle. Okay, so this is an important bad surface that Klein came up with, but this is definitely not his most important contribution to geometry. This is just one thing that you might have heard of that's named for him. So by far his most important contribution to geometry is what's known as Klein's Erlangen program, because it was undertaken while he was at Erlangen, and this is something he began in 1872. This completely kind of reimagined this basically completely reimagined how geometry should be done, or maybe providing an alternative way of doing geometry. So this completely inverted some notions of geometry. And introduced what's called group theory. Into geometric arguments. Now, group theory is, if you take like a 400 level course in abstract algebra as an undergrad, this group theory is kind of the starting off point for abstract algebra. There's a definition of a particular set of numbers, we'll say, or set of objects that satisfy a few axioms. So there's 3 group axioms that need to be satisfied to form a mathematical group. Okay, and groups are, I've mentioned them before in this class, but groups are basically, informally, they are ways to keep track of symmetry. They are related to notions of symmetry. Okay. And so group theory is introduced into geometric arguments, and the reason for this was that this allowed Klein to categorize all of these non-Euclidean geometries that were popping up. That were being discovered. And if you take Math 430, the course ends with basically a discussion of the Erlangen program. That's where Math 430 ends. Kind of. This would have huge implications even today in modern differential geometry. This is felt because it turns out that in a way this is the right way to do geometry. Now, what do we mean by that? So, if I had to describe it without any of the background and trying to give you just the best idea of what this Erlangen program was, the best way to describe it is the type of geometry that you want to do is determined by the transformations that you want to use. That's kind of a weird hand-wavy thing to say. So what do I mean here? Okay, so let's go back to Euclidean geometry real quick. So we look at Euclidean geometry. Okay, so it turns out that in Euclidean geometry, right, we are interested in things like, well, points, lines between points. Okay, we are interested, because we're interested in lines between points and things like this, we're interested in distances, right? Want to be able to compute the distance between A and B, right? Maybe we want to talk about angles, right? So maybe if I draw some other piece of line here, we want to talk about angles, right? So this is some angle theta. Okay. Now, what if I take this and I do something that Euclid called a rigid motion, right? So there's one example. Maybe I just slide it. Maybe I put my thumb down and I rotate it, right? Maybe I reflect it. You can't see that well because the paper's not super thin, but maybe I reflect it. So I draw some line that I'm reflecting it across, some mirror, and I reflect it across that mirror. Or maybe I do a combination of those things, right? So the question is, what changed, right? Well, nothing, right? So the only thing that changed, right, was the position of these things. So where the points were, so A, B, and C get mapped to points A prime, B prime, and C prime. Okay, so that changed, right? The actual like location of these points changed, but did the distances change, right? Did the distance from A to B change when I slid this over here? No. Did the distance from A to C change? No. Did the angle between AC and AB change? No. Right? So these angles and lengths are preserved by these rigid motions, right? So here, angles and lengths are preserved by rigid motions. Okay. Now, these rigid motions have another name. We call them isometries, or in this case, isometries of the plane, so isometries of R2. Okay, that's what these rigid motions are. Isometries, the Greek iso meaning same, metry meaning measure, so same measure, right? And that's exactly showing you that, well, these quantities, right, distance and angle are unchanged when I apply an isometry to the picture. Now, the old way of doing this, the Euclidean way of doing this, and the way that geometry was done all the way up to Felix Klein, okay, was to say I'm inherently interested in angles and lengths. Okay, and because I'm inherently interested in angles and lengths, and these are the quantities that I'm really interested in, because of that, it makes these rigid motions or these isometries interesting, because these are the transformations that preserve the quantities that I'm interested in. Okay, so what is basically the idea of the Erlangen program? The Erlangen program's idea is to go backwards. You start with isometries. So we'll denote that by the set isometries of R2. Okay, isom of R2. So the idea is you start with isometries of R2. Okay, and these are some functions, right? These, you can describe these in functional notation, or you can just think about them as being reflections, rotations, translations, glide reflections, combinations of those things, right? That's what these isometries are. There's a proof. You can prove that any isometry of the plane is at most 3 reflections. So if you like, you can view every single one of them as being some number of reflections. Okay, and you can think about that for a second to check with yourself that any complicated combination of translation, rotation, reflection, and glide reflection is just some combination of 1, 2, or 3 reflections. Okay, so that's the 3 reflection theorem, if you like. It doesn't really have a name. So the Erlangen program, the idea is to start with the isometries and say what quantities are fixed by the isometries, what quantities are invariant with respect to the isometries. Invariant meaning not changing. Well, angles and lengths. And then we say to ourselves, so the reason that angles and lengths are important is because they are the invariants of the isometries. Now, you might say, what is the benefit of doing that, and why does that blow everyone's mind? Why is that the way of doing geometry? Because this provides a much nicer way to think about all these different geometries that are coming up. So in the days of Euclidean geometry, and before the discovery of non-Euclidean geometry, there was only Euclidean geometry, right? There's no other type. So the discovery of non-Euclidean geometry means that there's multiple types of geometry, and hyperbolic is not the only type. There's also projective geometry that I didn't discuss very much, but I did mention Pappus's theorem, which was the first theorem in projective geometry, and I mentioned Desargues' theorem. That was, like the second theorem in projective geometry. So this provides a much nicer way to think about these different types of geometry. And what is that way? So the big fact: to change the geometry, you just change the transformations. You're studying. This is huge. What this means is that if you want to study Euclidean geometry, well, you do that by starting with the Euclidean transformations, these isometries of the plane, these Euclidean isometries of the plane. You study these and you are doing Euclidean geometry. If you change these, there's a way to change these transformations, okay, into these hyperbolic transformations or Möbius transformations. That we can talk about. If you're doing those sorts of transformations, or if you're studying those sorts of transformations, you're studying hyperbolic geometry. If you change this to be projective transformations, which I won't define, you're studying projective geometry. Okay, and Klein realized that projective geometry is a unifying most primitive geometry, in that these other types of geometries that you're doing can kind of be seen in a way as living inside projective geometry. So this is important to me specifically because in my PhD thesis, what I proved was a fact that was true in real projective geometry, or RP2 geometry. And this fact that I proved was known already in hyperbolic geometry. So I proved like a generalization of that. And the way that that works is that the thing that I proved is a generalization of that fact because hyperbolic geometry in some sense sits inside of the projective geometry that I was working in. Okay, so he was kind of the first to realize this projective geometry is important. What's an example of a way to see projective geometry? So imagine that we did, when we talked about compass and straight edge constructions, imagine we threw away the compass. So imagine we have compass and straight edge constructions. But we threw away the compass, so all we have is straight edge. All we have is this. What can I draw with this? What kind of figures can I draw? Right? Well, I can draw a bunch of lines. Okay. Do I have any way of knowing distances between points, right? So point here and point here. Do I have any way to know distances here? Well, no, right? Because in Euclidean geometry, if I'm thinking about this as the geometry of compass and straight edge, I had a compass, and I was able to open the compass up. That's the distance between A and B. I could compare that to other lengths, right? That's what gave me a way of measuring distance. So then, with projective geometry, right? What can I do here, right? You might think I can't hardly do anything, and so I can't talk about distances. Distances don't matter. What does matter? So distances don't matter. Angles don't matter. So what the hell, right? Like what is left to even talk about, right? The notion that matters in projective geometry are things like collinearity. Collinearity still matters, right? Go back to my discussion of Pappus's theorem, right? Pappus's theorem had something to do with a certain set of intersection points being collinear. So collinearity becomes the important thing. What's important in projective geometry is a notion or a quantity called the cross ratio. Okay, the cross ratio is a projective invariant. So remember I said invariant just means not changing. So if it's a projective invariant, the cross ratio is invariant. It's unchanged by projective sort of transformations. Okay, and this is the thing you can use to get everything you need. Now, what are the things you can do? I'm not going to spend the time to actually draw this. I'm just going to give you an example. And if you're interested in this process, let me know, and I can actually maybe show you the process on Monday of how you would generate this. But let me find what you can actually draw here. So what things can you draw with just straight edge? You can draw this, a perspective view of a tiled floor. You don't need compass to do that. You can do this with straight edge only. Okay. So as I said before, here's another example. This is the legitimate construction. Okay, so this is due to Italians. The reason why Italians have their name all over early projective geometry stuff doesn't have anything to do with Riemann, because this stuff was done before Riemann. This has to do with the fact that Italian Renaissance artists were some of the first to make use of perspective. Okay, and the study of perspective is the study of projective geometry. That's kind of the application of projective geometry, is in the study of perspective. Okay, here, to understand how perspective works, here's the perspective view of equally spaced points. We know these points are equally spaced, but when you view them with an eyeball over here, they don't look equally spaced. They look equally spaced, but if you actually measure, right, so if you're looking, going back to my picture, at these tiles, like I can clearly, if I outline these shapes, clearly they are of different sizes, right? So this is way bigger than, say, this one. But the way that they're drawn makes me believe that they could be the same size, same shape, even though they're definitely not. If I look at them, objectively, and I actually measure out here these lengths, they're definitely different. They're definitely different sizes, or even different shapes, right? And yet, it's an illusion, right, caused in my mind's eye that makes me view them as equal. Say, same thing here, right? These are equal tiles. Now, they're not actually equal if I measure them, but my eye sees them and inherently imagines that those are equal tiles. Okay, and so that's actually the first place that projective geometry popped up before mathematicians, well, other than Pappus and Desargues. Desargues, I guess, was in the 1600s, so the Italian Renaissance artists were doing this before him, but not before Pappus. And so anyway, David Hilbert, which is a name we're going to hear more of a little bit later. So David Hilbert actually showed that projective geometry alone is enough to build the usual basic algebra and operations that you're used to. So again, if you want to see that fully worked out, you should take Math 430, which is a course where this is actually done in its entirety. He did this in a book called The Groundwork, or the Grundlagen, I guess, which means like the foundation of geometry, like groundwork for geometry. Anyway, so he did he did a lot of work in showing that axiomatically you don't need that much. The projective geometry is enough to get you a ton of stuff. Okay, it's actually very interesting how this goes. And in that context, Pappus's theorem gives you commutativity of multiplication. So Pappus's theorem gives you commutativity of multiplication. Desargues' theorem gives associativity, I think. Gives associativity? Yeah. Okay, and so you can also study what are called non-Pappian planes or non-Desarguian planes, which don't satisfy either Pappus's or Desargues' theorem. Okay, so anyway, this kind of led to a revolution in how geometry was studied that still is being felt now, because this kind of turned a lot on its head, and it also brought the algebraic techniques in studying groups to bear on geometric problems, which is really nice. Okay, so I think I'll move on now from talking about Klein, but this is a really, really important thing. that happened here. So I mentioned previously, so on the foundation of analysis, I mentioned Carl Weierstrass. Okay, so Virustraff was born in 1815 and died in 1897. He actually left university without a degree and took up a teaching position just as a school teacher, teaching math, physics, I think even gymnastics. So his only doctorate actually came later as an honorary doctorate, but nevertheless, he is the father of modern analysis or calculus. So as I've mentioned several times, this is finally the point when all of the computations that were being done by Newton, Leibniz, Euler, the Bernoullis, all these earlier mathematicians was finally put on solid footing analytically. So he saw the underpinnings of calculus, realized that it wasn't really rigorous, there were some issues there, and so he formulated the modern definition of continuity. So if you've taken a course and you have seen epsilon delta definitions of continuity, this is due to Weierstrass. So formulated the modern continuity definition. So this is the epsilon delta definition involving these epsilons and deltas. And this is far more rigorous. This is actually a fully rigorous description of what is going on when you're talking about limits and continuity. And so if we're being really technical here, we'll say that, Carl Weierstrass is basically the person who, rendered an actual solution to Zeno's paradox fully. So this is like the first full solution Zeno's paradox is offered here. Otherwise, there's a little bit there's a little bit left to say. And so in doing so, he came up with something called the Weierstrass function that shows that the types of calculus and the types of analysis and types of assumptions that mathematicians were making before weren't on solid footing. Because the function, as I've drawn before, looks something like this. Okay, and this function is continuous everywhere. Okay, that's even with respect to Weierstrass's definition of continuity. This is a continuous function. Continuous, we'll just take the definition of if I'm drawing it, right, with a pen, I put my pen down, I draw something, and then I pick my pen up. Okay, so I don't lift the pen at any point. There's no holes. So it's continuous everywhere, but is differentiable nowhere. So this is called a nowhere differentiable continuous function. Okay, and as I mentioned last time, it looks like there are some pieces that maybe aren't as jagged as some of the other parts, but if you zoom in on those pieces, what you get is more jaggedness. So this is also an early example of a fractal. Okay, so this is a fractal curve. Okay, it has this self-similarity, it's got this jaggedness, and if you keep zooming in, it's just jaggedness everywhere. So there's no derivatives that you can compute here. The reason that this was such a problem is because up until Weierstrass, basically all of the math that was being done, all the analysis and calculus was being done, more or less assumed almost the opposite, that if you were dealing with a function that was continuous, then except for maybe like a finite grouping of points, or maybe it was infinite, but it was infinite in a suitable way, and we'll talk a little bit more about that later too, that you could deal with the discontinuity. Now, the way that the integrals, for instance, are set up, right? The way that Riemann integration is set up, you can deal with finite discontinuities, but you can't deal with infinite discontinuities. That's not manageable. Okay, so the infinite discontinuities part is a problem, but they basically more or less thought that almost every continuous function is pretty much differentiable almost everywhere except at maybe a few isolated points where it's nasty. Okay, and this showed that, well, that's not true. Here's a continuous function everywhere that has, it's like the exact opposite of that. It doesn't have a derivative anywhere. There's not a single nice point on this whole curve. Okay, so like this, the existence of this is the reason why real analysis is nasty. Okay, because it turns out that these types of functions are actually more common than the other types of functions. Okay, there is a way that you can prove rigorously. There is a notion for these being more common or these being typical. Okay, so these functions are actually more common than the functions you're used to. Because you might have a tendency to look at something like this and say, oh, this is pathological, right? This was clearly just constructed to throw a wrench into things, but in the wild, right, I'm using quotes here, in the wild, I'm not going to encounter a function that looks like this. But actually, the problem is that in the wild, most functions, knowing nothing else about them, look like this. So if you imagine every continuous function tossed into a hat, so that's a big hat, but every continuous function is tossed into a hat, and then you randomly reach into the hat and grab out a function at random, and you look at it. What does it look like? Is it more likely to look like the graph of sine x or x squared or e to the x, or is it more likely to look like this? There is a very rigorous way of saying that it's more likely to look like this. Okay. All right, so that's not great, okay, but this shows the need for being rigorous. Okay, so this shows the need for being rigorous. Benz, well, I mean, I guess technically there's a long theorem, but and there's a long formula, but of course, you know, I didn't name it after myself or anything. But, but yeah, I looked to make as many puns as I could when it came to that. So Weierstrass really finally put calculus and you know now what we call analysis on solid footing. So all of that underlying rigor was due to him, and so he proved the intermediate value theorem. You may remember from calculus. So the IVT, the intermediate value theorem, that was due to Weierstrass. He also proved what is now called the Bolzano-Weierstrass theorem, which if you take Math 410 at UMD, this will be one of the early theorems that are mentioned. So this has to do with some of the basic analysis and the basic structure of the reals. Okay, and so what kind of is being touched on here? Weierstrass, of course, is more concerned with the calculus we were doing later, but you know, he put the calculus on solid footing. Now, this is all touching on the structure of the real numbers. Okay. So the real numbers are a little tricky. They're not as simple as they sound here. So who were some of the people that did kind of big work here? Well, Weierstrass already did some big work, but even more foundationally than talking about functions and calculus, just how to construct the real numbers. There's a few ways. So you can construct them via Cauchy sequences. That's one way of doing it. That can be a little bit, there's a number of reasons why that can be a little bit undesirable to do it that way. There is actually a very simple and straightforward way of doing this due to Dedekind, so Richard Dedekind. So Dedekind was born in 1831 and died in 1916. Used the method of Dedekind cuts. So he used Dedekind cuts to construct the reals. What was his motivation to use Dedekind cuts? Eudoxus. I mentioned when we first talked about Eudoxus all that time ago that, many thousands of years ago, Eudoxus had essentially come up with the method of Dedekind cuts when he talked about his theory of proportion. So the theory of proportion, the same one that shows up in book 5 of Euclid's Elements, can be adapted to essentially more or less be the process of Dedekind cuts. Okay. So the method that Eudoxus outlined like 2,400 years ago is the one that basically works. So this is pretty amazing. It's a nice bookend to some of ancient Greek mathematics. Okay. So also, when it comes to the structure of the reals, George Cantor. Let me get his years. I can't remember off the top of my head. So he was born in 1845 and died in 1918. He showed, among a number of other things, Cantor pioneered early work on foundation of mathematics, specifically set theory, structure of the reals. So specifically set theory and structure of the reals. The most famous thing that he is known for is he proved that there are more real numbers than integers or rationals. So this is the hand-wavy way of saying it. The less hand-wavy way of saying it is that the real numbers are uncountable. Why is this a big deal? First, what does uncountable mean? Uncountable means that you're a set that is not the same size as the natural numbers. The natural numbers, or the counting numbers, being 1, 2, 3, 4, 5, and so on. Okay? And so the integers are countable. To see that the integers are countable, if I list out the integers, right? So if I think of a number line here, and here's 0, and here's -1 and 1, and here's -2 and 2, and here's -3 and 3, and so on. So the natural numbers are the numbers 1, 2, 3, 4, and so on, right? The counting numbers. So you have naturals, you have integers. They are the usual. It's so positive and negative integers and 0. So how do you count the integers and show that they're actually the same size as the naturals? Well, you think of a counting function, basically, right? You can probably come up with one quick. The idea is that you can count these in pairs so that really your method of counting is basically the same as counting here. So you count 1 and -1, you count 2 and -2, you count 3 and -3. You can think about taking this, folding it, and then counting like you would count the naturals. Okay. All right. Now I know that might not be the most rigorous description of how this works, but that's the idea. What about the rationals, though, right? The rationals don't seem like they are the same size. Seems like there's a lot more of these. What are the rationals? So rationals are, your P over Q, where we'll take the GCD of P and Q to be 1, so that these are fractions in lowest terms, right? Now, of course, any fraction we write down could be put in lowest terms, so this includes any fraction of integers, so P and Q are integers here. Okay, of course, Q is not 0, blah, blah. All right, there we go. But the rationals are also countable, so I'm not going to say how you can count them, but the hint is basically you can arrange them in an array, P over Q, right? You can arrange them in an array, so you can start listing out fractions here, and then you can kind of count them via this like snaking argument, okay? But you can't do that with the reals. And the reason why you can't do that with the reals is something called Cantor's diagonalization argument, which I might use to actually prove this, the same one that he used. I might use Cantor's diagonalization argument to prove that the real numbers are uncountable on Monday. But this is what Cantor did. So when Cantor first did this, it was met with a lot of hostility by some mathematicians, and it was even met with hostility by people had nothing to do with math. I think it was met with hostility by like some church leaders in Europe, which might be the last instance where church leaders anywhere were concerned with mathematical results. But Cantor, faced strict opposition from a lot of mathematicians, but Hilbert once said, "Let no one expel us from the paradise Cantor has created." Okay. And that illustrates how highly Hilbert thought of Cantor's work on foundational set theory stuff. Okay. And so a lot of work was being done at this time on kind of these foundational questions. So now toss away functions, toss away derivatives, integrals, and all that stuff you studied in calculus and get down to, the nitty gritty, like what is it that makes a set, right? Like what does it mean for the real numbers to be uncountable versus these other sets of numbers that are countable, and does this lead to any problem? Okay, and so even at a lower level, at a more primitive level than this, investigation started from some of these same mathematicians into the foundations of math as a logical framework, right? So really like the logical underpinnings of math. And so at this time, this is late 1800s, early 1900s. A lot of work, I'll say a lot of investigation was happening in the foundations of math. So Hilbert had done this big work kind of laying the solid foundation of geometry, of Euclidean geometry. So Hilbert's axioms that we mentioned forever ago when we were talking about Euclidean geometry, that was David Hilbert's way of putting the old Euclidean geometry that was done on absolutely like rock solid footing. So at this time, like it's not coincidence that other mathematicians wanted to do exactly that sort of thing for other fields. So one of the mathematicians that was doing work on this was Bertrand Russell, who you might know independently as a philosopher. So Bertrand Russell, he lived to be really old. I think he didn't die until the 70s. So Bertrand Russell, let's see, he was born in 1872, and died in 1970. Wow, yeah, so 1872 and died in 1970. Okay, so Bertrand Russell was a philosopher. He is well known as being one of the mentors of Ludwig Wittgenstein, who was also a very famous philosopher from the 20th century. So Bertrand Russell, though, did a lot of work in logic and foundations of math. And he set about trying to come up with this groundwork in the same way that Hilbert did for Euclidean geometry, and in the kind of the same way that Newton had tried to do for physics. He wanted to do the same. In fact, the work that he was working on when he discovered what I'm about to say was even called Principia, like Principia Mathematica, named after Newton's Principia. And so the story goes that he was working to publish the Principia, which was, it was supposed to be kind of the foundational work and logic that kind of showed that all of the underlying set theory and all the logic stuff worked out fine. And as it was going to printing, it was already being printed, he discovered a problem that invalidated basically the entire book. And this problem was known as Russell's paradox. Okay. Which can be stated quickly as let S be the set of all sets that do not contain themselves. And the question, does S contain itself? So, there's really only two options, right? It's a yes or no question. Let's say yes, right? Let's say that it does. Okay. Let's say it contains itself. But S specifically is the set of all sets that do not contain themselves. So an element of the set S necessarily doesn't contain itself. But we just said S contains itself. But if it contains itself, it cannot contain itself. So that can't be yes. So the answer has to be no. Right? But if S doesn't contain itself, well, it doesn't contain itself, which means it must be included in S, since S is the set of all sets that do not contain themselves. So if S contains itself, it doesn't contain itself, and if it doesn't contain itself, it contains itself. Now you might be content to say, well, such an S just doesn't exist, right? That saves us, right? But the foundations of set theory at the time said that there was absolutely nothing that should obstruct you from building a set like this. So saying the set doesn't exist is not even allowed. That's not even an answer, because this set was supposed to be guaranteed to exist, okay, by foundational set theory. But clearly, that's a problem. That poses a logical problem here. Okay, you might have heard this restated in a more informal way as the barber paradox. Right, so it's assumed that you have a barber. Barber is a man, and you'll see why that gets us out of this. Gets us out of this problem in a second. So the barber is barber of some village, and he shaves every man in the village that does not shave himself, and he only shaves the men that do not shave themselves. So then the question is, who shaves the barber? Right? There's only two options. The barber shaves himself. But if he shaves himself, he can't shave himself because he only shaves those men that do not shave themselves, right? Well, so then the barber doesn't shave himself. But if he doesn't shave himself, he has to shave himself because he shaves every man that doesn't shave himself. Right? So that's an issue. Now, again, sometimes this riddle is posed with a trick where the barber's a woman. So that solves it. Or, in these real world kind of applications, you could just say, oh, well, like such a barber doesn't exist. And that poofs us out of any issue, right? It's like, oh, that barber doesn't exist. There's no reason to even talk about it. So the difference is that when stated in set theory formally, at the time, set theory had some underlying axioms that meant that this set has to exist. And thus, there's a huge problem because this is just a contradiction sitting there in the foundation of set theory. So I'll talk a little bit about how that was resolved, where it leads. I'll even bring some Leibniz back into the discussion. And then that will be that on Monday. That will basically be our end of the course. All right. So, like I said, I'm still going to post your last homework. It's just going to be kind of a quick little exercise in brushing up on some of these names and some of these topics we've covered. So you don't have to worry too much about it. It'll be due plenty of time, so sometime next week. Your final exam will be similar in format to the midterm that you had. Midterm, I meant to actually upload the grades like a few days ago. I totally forgot, so I'll do that soon. So anyway, I will see you all on Monday.